Dr. Revis here. In this video, we're going to take a look at a half-life decay problem. Specifically, we're going to look at how much remains or how much has decayed. First, a brief review of half-life. For a more extensive discussion on this, see my other videos. Half-life is the time required for a radioactive element to reduce to half of its initial value. The time varies from element to element, and there are several isotopes on the periodic table that undergo radioactive decay. When an element or a radioactive isotope undergoes decay, it does it in stepwise reductions. In other words, there are half-life portions that occur through several stages. For example, shown here, we show the first half-life, the second half-life, the third half-life, the fourth half-life, and the fifth half-life. And you'll note that it reduces by 50%, 25, 12.5, 6.25, and 3.12. These are taken in half-life increments. Half-life never reaches zero. It forms an asymptotic curve. We can take a look at this in a tabulated form to understand it further before we work our problem. That's shown here. If we start at the initial concentration, that essentially means there's 100% of the isotope remaining and there's zero decay. Note that the remaining amount plus the percent decay must equal 100%. If we take this through one half-life, we note that 50% is remaining and 50% is decayed. Again, the remaining plus decay must equal 100. A second half-life leaves us with 25% remaining and 75% decayed. While a third half-life gives us 12.5, which is half of 25, remaining, and 87.5% decayed. And if we carry this on through the fourth half-life, followed by the fifth half-life, we see the values shown here. Again, remember that the remaining plus the decay must equal 100%. The fast way to remember is to start at 0, cut it by 1/2 to 50, then reduce that by half to 25, by another half to 12.5, to another 6.25, to another 3.12. Each reduction represents a half-life. First half-life at 50%, the second at 25%, the third at 12.5%, the fourth at 6.25, fifth at 3.12, and so on and so forth. So let's take an isotope from the periodic table. Let's choose uranium. And let's work through a problem using its radioactive decay. And here's the problem. A 115 milligram sample of uranium-235 underwent half-life decay. How much remains after 3 half-lives, and what is the total percent decay? We're going to take a look at this problem by looking at the percent remaining method, and we're going to take advantage of the table that we've already developed for the half-life decays. So at the third half-life, we would have 12.5% remaining, or 87.5 decay. The equation for this would be the initial mass or concentration. Note that mass and concentration are used synonymously. So the initial mass times the percent remaining, written in decimal format, equals the final mass. For our problem, we take 115 milligrams times 0.125, which is 12.5 divided by 100. That is, we convert our percent to decimal format. And when we do the math, we obtain 14.4 milligrams. 14.4 milligrams equals the proper number of significant figures of 3 for this problem. If we were to take a look at the percent decay would be the initial minus the final divided by the initial times 100. Therefore, for this problem, we would take 115 milligrams minus 14.4 milligrams divided by 150 milligrams times 100 to give us 87.5%. For simplicity, we have omitted the units from the percent decay calculations. Therefore, for our problem, a 115 milligram sample of uranium will have a concentration or a mass of 14.4 milligrams after 3 half-lives, which accounts for 87.5% of the decay. Let's just do one more problem here where we take a look at 5 half-lives. The math for this will be exactly the same. We take the initial mass times the concentration converted to a decimal, and we obtain that concentration from the table that we've already developed, shown here, the red line, and in the blue square for the remaining. And when we calculate the 115 milligrams times 0.0312, we obtain 3.59, which also has 3 significant figures. The 3.59 then represents the amount of uranium-235 remaining after 5 half-lives. If we'd like to determine the percent decay, we simply take the initial 115 milligrams minus the final of 3.59 milligrams divided by the initial of 115 milligrams times 100 to give us 96.9% decay. So, uranium-235 that starts with a concentration or a mass of 150 milligrams will have a mass of 3.59 milligrams, which accounts for 96.9% decay. Note again that this will never reach zero. It reaches an asymptote. So there you have it, a problem that allows you to see how to calculate the half-life decay of a radioactive isotope.